The word star has many different considerations in our life: a performer, an award, fame, even astrology. Yet, the one I love the most is the astronomical object. Just like a sun, there are various sizes, colors, and age of stars spread all across different galaxies. There are key spies to unravel the history and evolution of the galaxies they reside in. How do these massive objects come to be, with our sun being massive enough to fit 1.3 million Earths inside of it? And will these seemingly immortal bodies ever die? Do they age just like we humans do? In this voyage of ours, we'll be exploring how do molecules of gas and dust transform into these massive nuclear fusing bodies. We'll be looking at the evolution of stars. Now, the key defining feature for an object to be a star is to be sufficiently massive enough to ignite fusion in its core, which is basically when two light nuclei come together to form a single heavier nucleus. This happens because of the gravitational pressure inside the body itself. An interesting fact is that if Jupiter had been just a bit more massive, it would have had enough pressure in its core to start nuclear fusion and would have been classified as a brown dwarf. You can call it a failed star. Now, a galaxy of stars such as the Milky Way we reside in has an enormous amount of gas and dust in it, which is enough to make at least a billion of stars just like our sun. But if you want to find stars that are still in the process of formation, we must look where there's a large amount of gas and dust, the key ingredients for star formation. These are known as star nurseries, like baby nurseries on Earth. That's where stars are born. The star nurseries are giant molecular clouds that have cold interiors with temperatures of only 10 or 20 Kelvin, which is minus 253 degrees Celsius. That's extremely cold. And because of their cold temperature, most of their gas atoms is bound into molecules. The masses of those clouds can range from 1,000 times the mass of the sun to about 3 million solar masses. Now, for context, one solar mass is the mass of the sun, which is 1.989 into 10 to the power of 30 kilograms, which is about 300,000 Earths altogether. And the key idea behind star aging is the competition between gravity and pressure, two opposing forces. The force of gravity is trying to pull inward and compress the star, whereas the internal pressure of the gas molecules pushes outward, which causes a star to expand. It's like tug and pull. Now, in initial stages, the temperatures are extremely low, which causes low pressure, which is basically that the particles have less amount of kinetic energy, so they're not colliding with each other, which leads to lower pressure. But the low temperature causes a higher density. This means there's a higher gravitational attraction, causing gravity to win. Gravity wins and causes a huge collapse, which is needed to ensure that the star is dense enough and its core is hot enough to ignite nuclear fusion. Now, the period of a star, much before nuclear fusion occurs, in which protons combine together to form helium, it's given the baby name of a protostar. Now, obviously, it's very chaotic inside that piece of lump that's forming. Any sort of chaos or turbulence that takes place leads to angular momentum, tends to give even some part of it a spinning motion, even if it is very slow. Because of this, every collapsing core is expected to spin. Now, according to the law of conservation of angular momentum, a rotating body spins more rapidly as it decreases in size. Just like how when you're rotating on a chair and you bring your hands closer to yourself, you rotate faster because of the conservation of angular momentum. Now, this is exactly what happens when a core contracts to form a protostar. But even though it's spinning, it's not equal at every place. The poles spin much more slowly and the equator spins much more faster. So it's easier for the material to fall right onto the poles, which are spinning slowly compared to the equator, where materials are moving around more rapidly. So all the gas and dust falling towards the protostar's equator are held back by the rotation, and they form like a whirling extended disk around the equator. Like how you're in an amusement park ride that, where you stand back to a cylinder and then it spin fast. And as fast as it gets, you start to get pushed against the wall so strongly that you cannot possibly fall towards the center of that cylinder. Because of the same effect, the gas that's falling in towards the equator is held back and forms a disk of gas around that rotating equator. But gas can still, however, fall into the protostar easily from directions away from the star's equator, as it's not pushed back there, like the poles. But is there any way that a single star forming can ignite other more stars to also form? It actually can. When a massive star is formed, it emits a large amount of ultraviolet radiation and injects high-speed gas in the form of stellar winds. Now, this release of energy from the star heats up the gas around it, and which causes that gas to expand. All these hot gases come together to the surrounding cold molecular clouds near that star, which causes material in it to start compressing and which increases its density. If this density is large enough, gravity will overcome pressure in this case, and stars will begin to form in the compressed gas. Such a chain reaction where the brightest and hottest stars of one area become the cause of star formation next door occurs in many molecular clouds. We'll be looking at the stages of life of a star in our next voyage, where we will also explore the death of a star.